Okay. Okay. So we said that today we were going to. Can I make this smaller? Yeah. So give me a second. There we go. So we said that today we're going to start with like talking more in depth about the third technique that we mentioned yesterday for measuring complexity, and that was the infinitary first order language. This is a slide from yesterday. So let's go into more details into all these and prove some of the theorems that I mentioned in the lecture. Some of these theorems require quite a bit of work, so we'll probably spend quite some time on it. As I was saying yesterday, so please stop me with questions. Since I don't see your faces, I will not know if you understand it or not. So I guess I'm gonna use Rui Sui's face if he's following. Like I go. So Ruichi, if you're following, if your face is that you're fine, I'm gonna continue going. If you're puzzled, since I don't see anybody's face, so if I say something that is too complicated but he's fine, then otherwise please stop me and ask me for questions and I can slow down in the explanations. Okay, so let's review again. So by vocabulary, I just mean a set of symbols. Symbol meaning like symbols from constants, functions, and relations, like usually in first order logic. For our infinitary language, we're going to have our vocabulary that is, our like logical symbols that are the usual ones. And I guess so. This is like a big. So we're gonna sometimes use like a double and or just a big and a big or sometimes they don't need to be double to mean infinitary conjunction and disjunctions, so ands and ors. And let me just define them formally for you guys. So this language is going to be called L omega 1 omega. Okay, so I'm going to define it here. So a definition. So fix the vocabulary tau. So L omega 1 omega is the smallest class such that and it's similar to the definition of first order formula except for this infinitary part, and it's a small detail. That's why I want to write it down. So all quantifier free finitary formulas, tau formulas are in L omega 1 omega. If phi is in L omega 1 omega, or let me say phi and psi are so are the formulas not phi and psi, phi or psi that exists x phi for every x phi. So far we have the first order finitary logic. Now the third one is the third condition is the one that is interesting, and is that you can take infinitary conjunctions and infinitary disjunctions. This is a rule that we're going to use, an extra rule that I didn't mention yesterday, is that we only allow a finite tuple of free variables. We can only have finitely many free variables in every formula. Okay, so that's a condition that we put. We are, even though these formulas are infinite in length, because you can do a conjunction of infinitely many things, we allow only finitely many free variables. And that's to write that formally, it takes a little bit of work. So if X is a finite tuple of variables and S, including L omega 1 omega, is a countable set of formulas with free variables all with free variables in X bar, then the infinitary disjunction of I in S, well, of phi in S of phi and the infinitary conjunction of phi in S of phi are formulas. Okay, so this here means disjunction. Remembering this one is a conjunction. Disjunction, remember, it means or. Conjunction, remember, it means and. Okay, so I'm not saying anything too complicated here. I'm just saying this is the same as first order logic, except that you can use infinitary conjunctions and disjunctions, so long as you always make sure that you keep a finite number of free variables. So that means if you take an infinite conjunction, each of the formulas may have different free variables, but in total, you still need to have a finite number of free variables. Okay, so in this case, all these formulas that belong to S all of them have free variables within a fixed tuple X. That's how we guarantee that the conjunction and disjunctions are going to have free variables also within X. Okay, so we can only take a conjunction over a set S if all the free variables of all the formulas in S are included inside some finite tuple. That's what I'm saying. Good? So far, so good? Okay, so there are a few observations that we can make, and is that we can simplify these formulas and, well, somewhat simplify. And kind of to put just disjunctions to have them of the formula we were mentioning yesterday, where the infinitary part is outside and inside are we can put them in a kind of normal format, what I'm saying. Okay, let me just write that down better. Or at least just so observations. So if you have the negation of an infinitary conjunction of formulas phi sub I for I in S, let's say, this is the same as the conjunction of the negations of the phi sub i's, right? By the De Morgan laws, right? So that means we can always bring the existentials, the negations inside. Also, if you have, like, let's say, finite conjunctions, for instance, for I less than K of an infinitary disjunction for J in the natural numbers, let's say, of phi sub I J, this can be written as an infinitary disjunction of finitary conjunctions of formulas. Do you know how to do that? I guess there is how to do like a little trick. I guess you have to say for sigmas that belong to natural numbers to the K, conjunction of I less than K of phi of I comma sigma sigma I. Don't worry about the details there, but essentially, I mean, what I'm saying, and this is a countable set. That's the usual trick of when you have to move an existential and a finite conjunction or a finite disjunction. So the finite conjunctions can be moved inside, the same way the finite disjunctions can be moved inside. So essentially, we can all have like most of the structure on the quantifier free formula inside. And our formulas we have this shape up here. We can always end up writing them like this. Infinitary disjunction, existential, infinitary conjunction for all, infinitary disjunction, existential. And then most of the structure, the little ands, the finite ors, the negations, they are all within the quantifier free part inside. Okay, it's not going to be like this one. It's not necessarily n alternations. There might be like an infinite number of alternations branching in a tree. So it's not going to be exactly like this. But what we're saying is that in the kind of normal form, we can put like most of these formulas inside, and the outside just keep these guys. I don't want to go too much into this because I'm imagining that if you took a logic class, you know how to deal with formulas. Yeah. If you're fine with that. Okay, so I'll move on. So we mentioned yesterday, okay, so to be able to make sense of these formulas, to be able to use them, all we need to do is define in some way what it means for a formula phi to be true for tuple A in a structure capital A. I don't think I need, and this is what, when we write this like this. So A models phi of X. This is kind of the obvious thing. There is nothing special about this. Like the infinitary disjunction is modeled by one of the disjuncts is true in the structure. So I imagine everybody can understand what it means for a formula to be true. Just by adding infinitary doesn't add much. Okay, cool. So we did one example last time. Let's do one more example because we're gonna be using these things. We're gonna be using many examples. We have a lot of examples with linear orderings. So let's do one with linear orderings. So let's do one that says so in a linear ordering, L, which has a domain L and an ordering, we want a formula thin X comma Y that says that the interval is finite. Okay, so there are only finitely many things in between X and Y. How will you guys write that formula? So again, this is something that in first order logic you couldn't do. You can provide compactment, that there is no such thing. So the problem is that in first order logic, you can say there are 3 things in between X and Y. There are 5 things in between X and Y. There are 17 things in between X and Y. There are n things. If you want to say there are n things in between X and Y and nothing else, you can say there exists Z1 up to Zn such that X is less than or equal to Z1 or less than Z2, less than Cn, less than Y, and there is nothing else in between. And for every W if X is less than W less than Y, then one of these, then conjunction for I less than N of W equals CI. So W is equal to one of these CIs. Right, so this says there are exactly N things strictly in between X and Y. So if you want to say that there are finitely many, we have to say that for some N, infinitary, for some N in omega, one of these formulas is true, or the N formula is true.
You did a disjunction, I mean, in the final, I mean, there is a.
Thank you.
Yeah.
Thank you, Richie. Yeah. And the finite disjunction, but yeah, so one W is equal to one of the CI, so it's a disjunction. Right, so that's how you will write that. We good? Any questions so far? Understanding what these formulas look like? Cool. And then we mentioned two theorems that we want to prove today. And they are the following. So the first theorem, it says that if you have a subset, we're going to prove them almost like simultaneously. I guess we're going to prove this one first. But the first one says that if you have a subset of the set of tuples that is invariant under automorphism, in particular, suppose B is the automorphism orbit of some tuple. So B is a set of all the set of tuples that are automorphic to a fixed one. You can think of one of those sets, but actually this is true for any set that is invariant under automorphisms. There's going to be some formula with, I guess, k many variables. X is a tuple of variables and same as this, such that B can be defined by the formula phi. So B is a set of all tuples that satisfy the formula phi. So if you're automorphism invariant, then you're definable. That's how we can like write this as invariant implies L omega 1 omega definable. And of course, L omega 1 omega implies invariant. So actually, we have both. So automorphism invariant for a relation is the same as being defined. And the second theorem we're going to prove today, due to Scott also, same paper, is that for every countable structure, there is an infinitary sentence, which we're going to call the Scott sentence of A, such that for any other countable structure C, the sentence is true in C if and only if C is isomorphic to A. So essentially, this sentence psi is true about A and true about everybody isomorphic to A, of course, but not true about anybody else, so long as it's countable. Okay, and in this case, we're gonna say that if this is the case, you have such a formula phi, then we say up here psi A is a Scott sentence for A. Okay, so when we say a Scott sentence, it's a sentence that is true about A and not true about anybody else. So it completely recognizes A among the countable structures. Cool, so that's the goal for today. Questions so far?
We have a question in chat box.
Ah, cool. Let me find this. I lost the chat. Where is the chat? Oh, here. Yes, that's right. So, okay, so in the example, right, so the question in the example, if I understand right, is that whether we could write here instead of this, whether we could write that exists an n in omega and that exists Cn up to Zn plus 1, such that this is true. So let me tell you, so the answer is no. You couldn't say, so n cannot be a variable. And because if you look at this formula, this is not a first order formula because the length of this, the length of the number of variables that we use, and therefore the length of the formula, depends on the value of n. So if n were a variable, you cannot use its value inside the formula, right? In a formula, you cannot say the length of the formula cannot depend on the length of the variable. It's not a finite string. It's a string that depends on the length of this one. So it wouldn't really make sense. So all of these formulas for the different n's are different formulas. They're different first order formulas, and they have a different number of symbols. Like the larger the n, the more symbols these finitary formulas have. So they are different formulas. And the other thing that cannot happen is that these are formulas, these are first order formulas where the variables can only range over elements in the structure, right? So we are thinking of all of these guys belong to L. All the variables that we have belong to L. So we are not allowed to quantify over omega like that. But essentially we are quantifying over omega because when we say this junction like this, essentially we are saying that exists an n in omega. Except that it's not the same because of what I was saying, that the length of this formula will depend on the value of the n that we choose. So essentially for each n, we are taking a different formula. So yeah, so n is not really a variable. So this here, so these sub-indices here, it's just it's a different name for variables. We have n variables and we are calling them z1 up to zn, but it's not that the index is a variable. Ci is not a variable. Let's n can be arbitrarily big. Connects maybe infinite long first order formulas. Connects, I don't know what connects means there, but yes, n can be arbitrarily big. So this formula is going to be infinite. If you want to write this formula down, it's going to be infinitely long. Because, I mean, you can write this formula down. Let's put a name to the, let me copy. So let's call this formula, let's call it, I don't know, theta n. It says that exists and depends on x and y. So our formula that we are defining here, fin x comma y, if I write it down, what I'm writing is theta 0 x comma y, or theta 1 x comma y, or theta 2 x comma y, or theta 3 x comma y. This is a 2. Or dot dot dot, and I'm putting them all together. So yes, so this is a sentence that is arbitrarily big. It's an infinite sentence. It has infinitely many characters if you want to write it down. Right, so that's the same thing as infinitary disjunction over any omega of theta. Cool. Thank you for the question. That's probably useful for other students too. So yeah, this formula can get arbitrarily big, and in this case, it's only one layer infinite, but it could have that, it could be, as we're gonna see, that each of these ones is themselves arbitrarily big. So we can have infinite sentence that we just put together and so this infiniteness can get quite complicated. Okay, so we were looking at this, the theorems that we're going to prove today. Let's talk about the depth of formulas a little bit, because I guess that helps understanding what the formulas look like and how they behave before we go into the proofs. So we mentioned this yesterday. I'm just repeating from yesterday. So when you look at the complexity of a formula, you're going to look at the alternations of exist ors versus for alls and ands. Okay, so when you have an exist and an or, this infinitary disjunction, you put them together. These ones you put together. These ones you put together. Here you have 4 alternations right here, and maybe more in here. That's how you count the alternations. Okay, and if you start with or there exists, you put a sigma. If you start with and, you put a pi. So let's look at the examples that we have so far. There. So what are these formulas up here? So this one has an infinitary, the first one has an infinitary disjunction, and what is inside is quantifier free. So let's write it down. So this part up here is quantifier free. So the whole thing is sigma 1. Infinitary. The same is true here. This one is not quantifier free. Sorry, it's not quantifier free. This one here is no. What is it? So sorry, I'm getting confused. This one up here has a for all, right? So this is pi 1 because of this for all up here. That makes it a pi 1. And then here we have a disjunction of exist. So the whole thing becomes sigma 2 infinity. All right, so we have the disjunction, exist come together, and then the for all over there makes it up, sigma 2. And then this one here, we have here is sigma 1, and then we put the infinitary disjunction, makes it a pi 2. Yeah, everybody? That's how we count these alternations of modifiers. So these two are paired together because exist and disjunctions are paired together. But the for all is a different alternation. Good.
Can you have a sentence like infinite conjunction of, say, sigma 1, sigma 2, and sigma 3 convert to infinite clouds?
Yes. So you can have, for instance, suppose you have a formula phi 1 that is sigma 1, and you have a formula phi 2 that is sigma 2, and a formula phi 3 that is sigma 3, and phi 4 is sigma 4, and so on. If you do, for instance, the conjunction of all of these, which is the same as infinitary conjunction of phi I, then what you're gonna get is neither sigma 1, sigma 2, sigma 3. You're gonna get something that is pi omega. It's gonna be the next level up. Okay, so that's here is the definition in that case in general. I guess let me show you the pi beta formula first, which is the one that we just did. If you have an infinitary disjunction of 4 holes, and then the things inside are sigma gamma for gamma less than beta, then overall we have pi beta. And if you have these ones are pi beta, and then we have infinitary disjunction, here we have sigma alpha. Okay, so it's a disjunction of things that are of smaller rank. Cool. And I guess it would require a proof. I'm going to skip the proof. Every infinitary formula is going to be pi alpha or sigma alpha for some alpha, because the infinitary formulas have to be written from the bottom, from the ground up, using conjunctions and disjunctions and roles and exist. And eventually, there's going to be an ordinal level that you reach, countable ordinal where you reach the complexity of the formula. So I'd like to skip that if you guys are fine with that. Okay, we don't need to get into these ones so far. I want to do some examples of formulas that are high up. Yeah. So do you know what the well-founded rank is for a partial ordering? Do you guys know that? So let P be a partial ordering. And let rank of an element A in P denote sometimes it's called the well-founded rank of A in P. Do you guys know what that is? So the rank, this here is the definition of A is the supremum of the rank of all the B's for B below A in P plus 1. Yeah, so if your partial ordering looks like I don't know, like this. This guy has rank 0 because it has nobody below. So if you have nobody below, you're taking the supremum of the empty set at 0. Supremum of this one is nobody below. Supremum of the empty set is 0. But if this one is A, there is one element below. And then you take the rank plus 1. So all of these guys have rank 1, and these guys have rank 2. Right? Everybody's familiar with these kind of things? Luigi, what do you think?
Yes, I think people know. And we need a partial order to be well-founded first place.
Right. If the partial order is not well-founded, okay, so I'm gonna put it like that. That might be undefined in the case when it's not well-founded, or infinite or something. We can put an infinity if the partial order below A is not well-founded. We can assume it's well-founded. And then you can have infinite ranks, right? Because you can have, I guess if you guys know, maybe I'm repeating things that everybody knows. If you have a partial ordering that looks like 2 has 3 elements, and here 4 elements, and here 5 elements, and you have 1 element on top. So now this one has rank 0. He has 1 and 0, 2, 1, 0, 3, 1, 3, 2, 1, 0, 4. And then this one up here is going to have rank omega because it's above all the other ones, right? So you can have ordinal ranks for these things. Okay, so I want a formula. Let me write this down in black. So I want I'm going to call it size alpha with the variable x, such that this formula is true about a tuple A, if and only if the rank of A in P is less than or equal alpha. Okay, so it's a formula that says that A has rank less than or equal alpha. So it'd be good if people think about it for a second before I give you a solution. How would you write that's such a formula? And alpha is an ordinal. So this is for a given alpha below omega 1. An ordinal. So the way to write this formula is, so we define these formulas phi alpha by x by transfinite recursion. So we assume we have already defined all the previous ones, all the ones below alpha, and we use them to define phi sub alpha. That's what transfinite recursion means. So we let phi alpha of x be the formula that says essentially you have rank less than or equal alpha. If you look at the definition, to have rank less than or equal alpha means that everybody below must have some rank strictly less than alpha. So below some beta that is strictly below alpha. Yeah, so that's gonna be the formula for every y less than x in P. Well, the rank of y is some ordinal that is below alpha. And how do we say that? We're going to do a conjunction, and it's going to be an infinitary conjunction of all the betas below alpha of psi beta y. No, sorry. This junction. All right, so this part up here is saying that the rank of y is strictly below alpha, right? I'm saying for some beta below alpha, you have rank less than or equal alpha. So this one up here by induction is saying that the rank of y is less than or equal beta, and all the betas are below alpha. So here is like a strictly less than or equal. So if I know that every element below x has rank strictly below y, I know that the rank of x has to be less than or equal alpha. So the claim is that the phi is what we want, how we want. Phi alpha P models phi alpha A if and only if the rank of A is less than or equal alpha is proved by transfinite induction. So you assume this is the case for all the previous ones, for all the phi sub betas up here, and then you prove it for us. Luigi, what do you think? Should we do that proof? I think it might be clear for, I don't know if it's clear for everybody or for most people.
I think it's clear, and we can do it in our reducer.
Excellent. Okay. So that's okay. So the next thing I want to ask you guys, the next exercise, this to do once because is what is the complexity of this formula? What is quantify alternation of this formula? Let me copy the formula. Okay, so that is the formula. So what is the quantified complexity? So let's see. First, I guess phi 0. We need to start with. I didn't do the inductive case. So phi alpha x phi 0. What is phi 0 of x? This means rank the x is less than or equals 0. So this is there is no y's below. In this case, there is no y, no betas below alpha. There is nobody's below alpha. So this formula is that this not exist y below x, right? That's what having rank 0 means. Sorry, less than or equal 0. Right? This is like slightly. I mean, it's a particular case. In the case when there is no such betas, you can say this is always false. But this junction over the empty thing is false. It doesn't matter. So this is the case 0. The case 0 is the inductive case. So this is pi 1. What about how do we keep on going? We want to keep on going. Phi 1 x is the formula. Now let's just write down what it is. If for every y below x, there is only one beta below 1, right? It's only one possibility for beta, and that's beta 0. So this is here we're using this is the alpha. For every beta below 1, phi 0 of y. That's what we're saying up here. Now, yeah. So this is still it's funny thing that's still okay. I think I'm making myself life too complicated. So this is still pi 1. Right? In general, if I write phi n of x for every y below x, phi 0 of y or phi 1 of y or phi n minus 1 of y, this is each of them. This one is pi 1. This one is pi 1, and then you can prove the next one is pi 1. So all of these is still going to be pi 1. We're not getting too big yet. But when we want to do phi omega x, now we want to say for every y below x, this junction of n in omega of phi and y and now this one, each of these ones are pi 1, but then this whole thing is sigma 2 because you have a disjunction, infinitary disjunction. And then the whole thing is pi 3. Yeah. So what's going to happen is every time we do another omega step, we're going to add 2 more. So we can be a bit smart on doing this. Maybe I'll skip this one so that we can move. I'll leave it for exercise for you guys. Well, it's in the book, but maybe if you don't read it and try it in the review session. So exercise for each ordinal alpha, there is a infinitary sigma 2 alpha formula phi su sub omega alpha such that P models the formula phi omega alpha and an element A if and only if the rank of A in P is strictly less. In this case, the sigma happens in the strictly less omega times alpha. So I guess we're doing sigma instead of pi like in the one before because we're doing strictly less instead of less than or equal. What you can see is that we are going up by omega steps here, and the complexity of the formula is going up by 2 every time. So when I increase alpha, like 1 more element, I'm considering that ranks omega elements more, but the complexity is going by 2 more. Okay, so I'll leave you guys with this exercise, and I want to prove something that is very similar.
So I have a question.
Yeah.
Why do you define this? Why don't you define this as pi 1? Why do you define sigma 2 if there are infinitely many disjunctions? Then you define it as sigma 2, not just of pi 1.
Sorry, I'm not getting that.
Because it looks, for this formula, it looks strange. For every n it's pi 1, then why not just generalize to arbitrary ordinals, say it's pi 1?
Well, no, we need this disjunction. This disjunction.
Yeah, well, I know you need this disjunction, but why don't you just define this as a pi 1 formula? You define this as a sigma 2 formula. Is there a reason to say this is sigma 2, not pi 1? Why don't you define this as a generalized pi 1 formula?
A generalized pi 1 form. Oh, you mean like change the definition of what it means to be sigma 1?
Right.
Well, okay, so if you define everything to be pi 1, it wouldn't be very helpful. Okay, but no, what you mean, what's matching your question is if you compare like the set of, if you look at the space of structures and you look at all the structures that satisfy the sigma 2 formula defined this way, this is exactly, it's a set that is going to be like sigma 2 in the Borel hierarchy, and it's going to coincide with the sigma 2s in the Borel hierarchy.
Yeah.
So this way of defining it matches the Borel hierarchy.
Okay, I see. Okay, sorry.
Okay, so let's do this example. And when I say it's the same, it's a very similar thing. I'm going to copy this thing up here. Ooh. For each ordinal alpha, there's a sigma 2 alpha formula such that sentence. Well, okay, I'm gonna do formula. I'm gonna write as phi omega to the alpha x comma y, two variables, such that on a linear ordering, L is gonna model this formula phi omega alpha x comma y, if and only if the interval x comma y in L has order type strictly below omega to the alpha, the ordinal omega to the alpha. Okay, how are we with the ordinals omega to the alpha? If you have an ordinal alpha, the operation omega to the alpha, Ruichi, should we define that? Should we review that on the side?
I don't think so, but does anyone have the question? What's the definition of this ordinal? I think you can ask. If not, I think we can.
If you want omega to the alpha plus 1 is omega to the alpha times omega. That's essentially the definition. For a limit lambda, omega to the lambda is the supremum of omega to the alpha. And omega to the 0 is 1. Okay, so I'm saying the formula that order type less than omega alpha, this means that the interval is well ordered and is an ordinal, it's a well ordering of order type strictly below omega to the alpha. And I'm saying we're going to find a formula which is of this complexity that has this property. How will you guys do that? So the idea is use transfinite recursion again. And then, so there is two cases. So if lambda is a limit, then phi omega, oh, I don't know what that was. Phi omega to the lambda is the same, well, x comma y. If lambda is limit, being strictly below omega to the lambda is the same as being below omega to the alpha for some previous alpha. So that is the same thing as the disjunction for alpha below lambda of phi sub omega to the alpha. Okay, and if and then for the case alpha plus 1, phi omega to the alpha plus 1, which is the same as omega cos of x comma y, if and only if you are, for some n in omega, the interval between x and y is below omega to the alpha times n. And we haven't defined those. These are a new kind of formulas. All right, so the interval is below omega to the alpha plus 1 if and only if it's below omega to the alpha times n for some n, where phi omega to the alpha times n of x comma y says that the interval x comma y is below, so less than omega to the alpha times n. How do we write that formula? We're going to write this one as follows. So this one says that whenever we partition for every z1 up to cn, if we partition, if we have that x equals z1 less than z2 less than zn equals y. So if we partition the interval x comma y into n pieces, one of them has to be less than omega to the alpha. For I less than n, the interval between zi and zi plus 1 must be below omega to the alpha. Okay, so that's saying that the whole interval has size less than omega to alpha times n. Whenever you partition into n pieces, one of them is below omega to the alpha. Cool. And again, if you need more time on that, I guess in the review session, you can look into that. And then, okay, so that to prove that it works, you use it transfinite induction. And then the other thing you had to prove to see it is that it has the right complexity, sigma 2 alpha. And then again, you do that by transfinite induction. Okay, so if this one up here is sigma 2 alpha, then this one up here is pi 2 alpha plus 1 because you got it for all up front. So that means that this one pi 2 alpha plus 1, and therefore the infinitary disjunction you get sigma 2 alpha plus 2, which is what you should get, right? Because here we have alpha plus 1. And in this case, if each of these is sigma 2 alpha, then the disjunction of all of them, in particular, they are pi 2 alpha plus 1, is going to be sigma 2 lambda. Well, sigma lambda and sigma 2 lambda are the same thing. So you can prove by transfinite induction that they have the right complexity. Okay. Cool. How are we going to do it in time? They're pretty good. I want to tell you a few. I think we're good for example. Any questions? Okay, so that was kind of like the intro I wanted to give for infinitary language, and now I'm going to go into like a real proof. What is this thing? To prove this theorem, Scott's theorem. So let me go to the end. Oh, we can do it. Of this section. So you guys have it in order when you're gonna see these things here. And then we can prove Scott theorem. So this is the theorem, I mentioned it before. So theorem for every structure, countable structure A, everything is countable. There is and L omega 1 omega sentence size of A such that A models size of A, and if any other structure model C models size of A, then C must be isomorphic to A. And then this again is countable, and then this is countable. And this size of A is said to be a Scotch for A. There can be a structure can have many Scotch sentences, and one of the ways to define rank that we saw in the last class was look at the simplest formula or the simplest complexity for a Scotch sentence. So there can be many Scotch sentences. They are recognizing A uniquely. Look at what the simple one is, the simplest in terms of complexity. And we saw some examples of this. Right here, for instance, Q, the ordering Q with less than is a unique, countable, dense linear ordering with no endpoints. So in the language of linear orderings, you can say that you're dense, meaning for every two elements there is one in between, and they have no endpoints. For every point there is one to the right, and for every point there is one to the left. So that's a sentence. It's actually a finitary sentence in that case. In this case, is finitary by 2, and it's true only on the rational numbers among countable structures. Actually, there are uncountable structures, and there are many different ones that satisfy this sentence too. And in the case, it's not unique. But in the countable world, Q is the only one that satisfies this sentence. For the integers, you can write the sentence that says that it has the linear ordering, it has no endpoints, and the interval, and for every 2 points, the interval in between is finite. We saw how to write finite before, and you're gonna end up with an infinitary by 3 sentence because saying finite is infinitary. That is only true on the structure of the integers, on the linear ordering of the integers. So that's a Scott sentence for the linear ordering of the integers. And we can define Scott sentences for ordinals using the formulas we defined in the example, but we'll do it after we prove the theorem. Okay, so if there are no questions about this statement, so I'm gonna need to define these formulas, and I'm gonna need to talk about this isomorphism. So I need a tool called the back and forth set. And so let me introduce this tool that we're gonna use in these proofs. So definition, so given structures A and B, a set of tuples, it's a subset of A less than omega times B to the less than omega. Actually, A times B, tuples of the same size, I guess. Maybe it's better the other way around. Has the back and forth property if it satisfies the following properties. If whenever for every pair A comma B that belongs to I, okay, so I'm thinking of I actually, I'm thinking of it as a subset of A to the less than omega times B to the less than omega, both tuples of the same size. So for every I in there, you have three properties. The atomic diagram of A in A is equal to the atomic diagram of B in B. Okay, this is not exactly what I want. I'm gonna say, I'm gonna erase this. So the atomic diagrams, instead of all the atomic formulas, true about these tuples, and I want them to satisfy. Whenever you have two tuples in I want them to satisfy the same atomic formulas, but infinitely many is too many. So what I'm gonna say is A and B satisfy the same quantifier-free formulas among the first few many, among the first, let's say, lengths of A many. Okay, so forget about the part that says among the first few many. So I wanted to satisfy the same quantifier-free formulas, these two tuples, one in A and one in B. But I don't want to use all the quantifier-free formulas. So the quantifier-free formulas can be enumerated in a list. You can enumerate them. I mean, there are countably many that you can write. Or we can even say atomic formulas. Here, let's do atomic. You can enumerate atomic formulas in a list, and we don't require to satisfy all the same atomic formulas, just the first few many. How many? Well, let's look at the lengths of these tuples, the tuple A, and let's say those many. So if A gets longer and longer, then we look at more and more atomic formulas. Okay, and then I'm gonna say for every B in B, there is C in C in A, such that A, C, comma, B, D belongs to I, and for every sorry, this is C in A, there is D in B, such that A, C, B, D belongs to I. So these are the back and forth property that up down there, and they are saying that if I know tuple AB is in I, and I want to extend this, put an extra element here, I can find a C here, such that the pair belongs to I. And if I want to extend, if I have a C up here, I want to extend that one. There's a way to extend this tuple here with a D, so that we are in I. So that's what is called the back and forth property. So we can put back and we can go forth. Okay, so this is a very important property. And the main lemma is that if I, subset of A to the less than omega times B to the less than omega, has the back and forth property, then again, if A, comma B belongs to I, or for every A, comma B in A, there is an isomorphism F from A to B such that f of A equals B. Okay, so that's the main lemma about these back and forth properties. If you have such a set that has the back and forth property, and we have a pair of elements inside, then we can build an isomorphism from A to B that maps tuple A into tuple B. Ricky, do we? Okay, so let me do a picture proof for this. So the way to build the isomorphism is you start mapping. So a picture proof. So we need to build F, and we're gonna start mapping A. So let me draw. Here is A, here is B, and let's call this one A0 and B0. We want to map A0 to B0, so we start by defining mapping a map from here to here, just mapping them up. And then we want to extend this to an isomorphism. So what we want to do is extend this tuple a little bit, add one element, and let's call it B1. So we just add one element. By the back and forth property, we can find an A1 up here such that A1, B1 belongs to I. So we know A0, B0 belongs to I because that was our assumption to begin with. And then by the back and forth property, whenever I have a D that extends B, I can find an element C in this side such that this pair is in the back and forth set. So I extend this tuple and I find an extension of this tuple. So that's in the set. And then what I do is I extend this tuple by one element, I add one element to the tuple, and I look for an extension of this one such that A2, B2 belongs to I. And then I'm just mapping them in the right way. And I keep on going. And I make sure I consider every element of A and every element of B at some point during the construction. I'm going to end up with an F up here from A to B. There's going to be a bijection. And along the way, all the tuples we define along the way, AN and BN, they always belong to I. Why is this bijection an isomorphism? Because a bijection doesn't imply isomorphism. In principle, doesn't even need to be bijection, let's say. And the reason why we're going to get an isomorphism is that whenever we have a tuple that belongs to I, satisfy the same atomic formulas. These two tuples. So AN and BN satisfy the same atomic formulas among the first n many, or n plus the length of A0 many, I guess. So the longer the n, the more formulas we're considering, and eventually we're going to end up considering all the formulas and all the elements. They are always going to satisfy the same formulas on the A side or on the B side. So we end up with an isomorphism. Good. Cool. Excellent. So maybe it's no, let's do 15 more minutes and then we do a break. So let me do one now interesting theorem. Yeah. Well, I guess it's called a lemma here. Now we start dealing with infinite logic. So here it is. So the lemma is the following. Let me just look at the notes. So if two countable structures let's call them A and B satisfy the same L omega 1 omega sentences, then they are isomorphic. Okay, so if two structures satisfy all the same L omega 1 omega sentences, they must be isomorphic. So this is not true in first order. In first order, we can have structures that are elementary equivalent, meaning they satisfy the same finitary first order formulas, but not isomorphic, right? So elementary equivalence or first order doesn't imply isomorphism. But in the case of countable structures and L omega 1 omega, yes, elementary equivalence for L omega 1 omega implies isomorphism for countable structures. Okay, so let's prove this. So we prove this thing about the back and forth set for a reason, and that's how we're gonna, because that's what we're gonna apply right here. So let I be the set of all pairs of tuples A comma B that belong to A less than omega times B less than omega, such that satisfy the same L omega 1 omega formulas. Okay, so we consider the set of pairs of tuples which satisfy the same L omega 1 omega formulas like I saw A in A and B within B in the respective structures, right? And then we claim that I has the back and forth property. This will be enough. This will be enough for what we want, because so this is enough because our assumption is that A and B satisfy the same L omega 1 omega sentence. This means that by assumption, the empty tuple belongs to I. Right? They satisfy the same formula, meaning the same sentences. These are empty tuples. So, and so we will have an isomorphism from A to B, right? By the lemma on the previous slide. If you have the I satisfies the back and forth property, then there is an isomorphism from A to B, mapping the corresponding tuples that we have in here. In this case, the empty tuples. So we don't have any requirement. Okay, so what we need to do is prove the claim. Cool. So okay, so we need to prove the properties of back and forth sets. What are the properties? Let's call them 1, 2, and 3. So 1 says that these tuples, if two tuples, okay, so this is for A, comma B in I. So if you have A, comma B in I, then the first one says that they satisfy the same atomic formulas among the first few men. Is this true? Well, the way we define the set, yes, to belong to the set I, you need to satisfy the same L omega 1 omega formulas, not just the atomic formulas, but to be in this particular case, you need to satisfy all the L omega 1 omega formulas. So in this particular I, for sure, A and B satisfy the same atomic formulas. You satisfy much more than that. So that's pretty easy, right? So let's consider 2. So suppose 2 is false. Let's go read what 2 says. 2 says for every B in D, there is a C in A such that these extensions belong to I. Suppose this is false. So suppose there is a D in B such that for every C in I, C in A, the pair AC BD does not belong to I. Towards a contradiction, we're going to reach a contradiction. Suppose there is no way to match this D. There's no way to match the D. There's no C that matches the D. Okay, so how are we going to get a contradiction from here? So for each, let me write this here so we have more room. So for each C in A, we know that this tuple doesn't belong to I. So that means that there is a formula L omega 1 omega formula phi sub C that's true of let's say X, Y, such that is true such that B models phi C on a BD, but A does not model this formula. Okay, so what I'm saying here is if this pair of tuples is not in I, by definition of I, it means there is a formula that is true about one and false about the other. Right? That's what it means to be not in I. So, and then, so for each C in A, we know that this guy is not here. So for each C, we have a formula that's called phi sub C that is true about BD and false about AC. Okay? Cool. But now, consider, I'm gonna go and copy this to the next slide. But now consider the formula psi of x bar, which is going to be there exists a y such that infinitary conjunctions among c's in A of phi c of x y. Okay, so C up here, it's not a variable. This is just indexing the formulas. It's just used there for indexing the formulas, right? For each C, there is a different formula. So the phi sub c is still there, it's just indexing the formula. So then what's up with these formulas? Then B models psi of B as witnessed by D. Because right here, so for every C, BD satisfies the formula. So if you put D equals Y, this one is your Y and this one is your X, then you satisfy them all. But A models the negation of psi B, of psi A. Because for every C that you choose, one of these formulas is false, namely phi sub C. Because for every C, we have A models not CC AC. So A models not the conjunction over all C's in A. A models for every Y not conjunction. Which is the same as. Yeah. So, but then this would imply or would contradict that AB was chosen to be inside I, right? Remember, we started with AB in I, and if they are in I, they might satisfy the same formulas. But here we found a formula that is true about B and that is false about A. So that would be a contradiction with the fact that we chose. So the fact that we couldn't choose, we couldn't find the matching tuple, led us to a contradiction. So that means that for every D, there must be some C such that you get this tuple to be inside it. Okay, cool. Number three up here is completely analogous. It's just the other way around. So the proof is exactly the same. Okay. So that proves this lemma that if you have two countable structures that satisfy the same L omega 1 omega sentences, they must be isomorphic. Okay, I think this is a good time to have a break, 15-minute break.
Yes.
So I have a question.
Yeah.
Why empty belongs to I? Because they just satisfy the same sentence, not the same formulas. You didn't say, you didn't assume they satisfy same formulas.
Oh, you mean why empty? This is what you said. Why empty set, empty set?
Yeah. Why?
Well, but here is an empty tuple. By empty set, I mean the empty tuple. A formula about the empty tuple is a sentence. That's what a sentence means, no? A sentence is a formula where there's no free variables, or the free variables are the empty tuple.
Okay.
Yeah.
Okay.
So I mean, if you want, what I'm writing by here, I mean the type, the L omega 1 omega type
Nice.
A
Oh, yeah.
equals
Right.
the L omega 1 omega
Right.
type
Okay.
of B.
Okay.
Any other questions? It's a good point to ask questions about this proof. Okay, so let's do like yesterday until 45. Richie?
Yes. Then we come back at 45.
Cool. Okay, whenever you guys are ready.
Antonio, I think you can start now.
Let's wait for Luigi.
Okay.
No?
I don't know. I called him and I don't know where he's now.
Oh, there you are. Luigi. Should we start?
Yeah, let's start. Sorry. Yeah, let's start.
Okay. So welcome back, everybody. Are there any questions from what we were doing before we move on? Okay. So the lemma I want to prove now is that every automorphism orbit is definable in L omega 1 omega. So we have again a countable structure A, capital A, calligraphic capital A. And we want to show that the automorphism orbit of a tuple little a is definable. So for every tuple little a, there is a formula, infinitary formula that we call phi sub double a. So the double a here is just an index for the formula. The formula has three variables x. such that the formula is true about a tuple B if and only if the tuple B is automorphic to A. Okay, so in other words, this can be written as the automorphism orbit of A bar can be defined as a set of all B's that belong to A to the length than A, such that A models phi of B. So the automorphism orbit of A is defined by that fact. So every automorphism orbit is defined. That's what that says. And then this is one of the lemmas that we had up there. I don't know why it's so hard to move. Oh my goodness. Okay, maybe I shouldn't have done this. Oh, there we go. Yeah, here. Every automorphism invariant set, in particular automorphism orbits, is definable by some formula phi. That's what one of the lists. So if you're invariant, we're gonna prove this one next. I guess this is a corollary of this lemma that we're doing right now. Okay, so let's prove this lemma. This is actually quite easy. So we know that if AB is not isomorphic to AA, there is a formula size of B, let's say, let's call it A comma B, such that is true let's call it a sentence. Let's write a sentence because that's what we know so far. Such that this is true here and AB satisfies the negation of size of AB. Right, because we proved in the previous lemma that if two structures are isomorphic, then if two structures satisfy the same sentences, they must be isomorphic. So if they are not isomorphic, there must be one sentence that is true in one and not true in the other. So these are sentences in the structure that have a constant for A and B, right? So we can think of this of psi of AB as a formula psi AB with variables x such that in A we have psi of AB holds of A, but the negation holds of B. Right, I mean, this one is, these are sentences in the extended structure which have constants for these guys. So we have like an extra set of constant symbols that we are interpreting as A or as B. So those are, we can think of them as the variables. Right? But then we let phi of A, the X, be the conjunction over all these in A to the length than A, such that B is not automorphic to A of psi AB. So note that this formula phi A is true of A because all these guys are true of A for all the B's. For all the B's, these formulas are true. For all the B's in here, these formulas are true of A. And if B is not isomorphic to A, automorphic to A, then A models the negation of CA. Because there is one of the formulas in the conjunction, namely the one that corresponds to that particular B, that that makes it false. And if it's true about a tuple, it's true about everything that is automorphic to it, because the automorphic tuples look the same from a structural viewpoint. So this sentence is going to be true of everybody that is automorphic to A and false of everybody that is not automorphic to A. Okay, so we define it on purpose so that it's false on everybody that is not automorphic to A, and we don't need to do anything for the ones that are automorphic to A, because if it's true about A, it's true about everybody that is automorphic to A. Luigi, make sense? Cool. So that means for each tuple, we have a formula that is true about the tuple and everybody automorphic to it and about nobody else. And if you look here, let's prove the next lemma that we had in there. A corollary. If B, sorry, Roman B is a subset, let's call it R. It's a subset of A to the K, is automorphism invariant. Or closed under automorphisms, then is definable in L omega 1 omega. L omega 1 omega formula phi that defines R. A tuple A belongs to R if and only if A models phi A. R is definable by this formula. And what is this formula phi? Let phi dx. I mean, if you are automorphism invariant, you're a union of automorphism orbits, because every orb, if you're automorphism invariant, if you contain an element, you contain everybody on the orbit of that element, because the orbit are the places where the automorphisms take that element, right? So let's just write that down. Every automorphism invariant set R like this is a union, and it's a countable set. It's subset of a countable structure, so it's a countable set. It's a countable union of automorphism orbits, right? Because if it contains an element, it contains everybody in the orbit of that element. A tuple, it contains everybody in the orbit of the tuple. So then, if we can define each of these automorphism orbits, we consider a formula that is the union of these ones, or the disjunction of these ones, and we get a relation that is the union of these orbits, right? So we let phi sub x be the disjunction for A in R. So take all the tuples in R of the formula phi sub A of x, where phi sub A is the formula from the previous line, the one that defines the orbit. Phi sub A is the one that defines the orbit of A. Right, so now everybody that is in R is going to satisfy one of these formulas, namely the one that corresponds to itself. And if you're not in R, then you're not automorphic to any of these guys, so you don't satisfy any of these formulas. Yeah, so this disjunction up here is just saying take the union of all the orbits of all the elements of R. And that's a formula that is true only about the things in R. Make sense? Cool. So let's go back to what we had back there. We're here. So this is a theorem that we had that by there. Every automorphism invariant set is definable, and we can use these to measure the complexity. Or what is that definition? I think that comes later. Up here. Yeah, so the orbit rank of a structure A is the least alpha, such that every automorphism orbit is sigma alpha definable. So now we just proved that every automorphism orbit is definable in L omega 1 omega. That's what we just proved. So there must be an alpha such that they are all sigma alpha definable. Let's take the supremum of all this, the complexities of all the definitions. And that's your orbit rank. Notice that if all the automorphism orbits are sigma alpha definable, then the union of orbits are also sigma alpha definable because we're taking these junctions. If you take a union, we take this junction. So this is essentially the same as saying is also the least alpha such that all automorphism invariant sets, relations are sigma alpha. So not just the orbits, but all the automorphism invariant sets are sigma alpha definable. And those are all the sets that are definable actually, because to be definable, you need to be automorphism invariant. So actually this means that all the definable sets inside the structure A are sigma alpha definable. And this least alpha is the rank. So it's a pretty robust notion in that sense. Cool. So the other definition of rank that we had is the Scott rank, the Scott sentence rank, which is the least alpha such that there is a pi alpha plus 1 Scott sentence that is true, a sentence that is true only about A. So we need to prove this one. We haven't proved this one yet. So let's now finish our the day-to-day proving that there is a sentence that is true only about A. And that was how we started the second hour today. This is the theorem that we want to prove for every structure A. There's an L omega 1 omega sentence size of A that is true about A. And that is, and if it's true about somebody else, that somebody else must be isomorphic to A. So let's write that. Let's write that sentence. Let me just copy this. And such a sentence is called a Scott sentence for A. I said this before. Let me just copy this and put it in a new slide. Okay. So proof. Okay, so as before, so for each tuple A in A to the less than omega, let phi sub A define its orbits. As in the previous layout. Okay, so now here's the intuition for this. So given a structure B, consider the set I, which is the set of all the pairs A comma B, such that B models the formula that defines the type of A. Oh, and I guess on the side, let's just define for the empty tuple B, the formula is always true. The empty tuple is always it's only automorphic to itself. It's only one empty tuple, which is the empty tuple, and the automorphic. So empty tuple is always true, just to make this definition work out. Okay, so we said the set of all the pairs. So given another structure B, the set of all the pairs such as B satisfies the formula that defines the orbit of A. If you were going to consider, but this is, so phi defines the orbit, let me just write it down here, of A in A, but not in any other structure. Just we only know that phi A works inside structure A. So we don't really know what phi A does on a different structure B. But hopefully it's gonna do the right thing. So the claim is that A is isomorphic to B if and only if I has the back and forth property. Well, I don't think we need to there's much to prove. If I has the back and forth property, then we'll prove already that that implies that A and B must be isomorphic. Well, notice that the empty tuple and the empty tuple, the formula for the empty tuple is always true. So the empty tuple belongs to I. So we always have empty tuple in I, because formula for the empty tuple is always true. So if it has a back and forth property, then A is isomorphic to B by the property of the back and forth sets that we defined before. And conversely, if A is isomorphic to B, then in that case, we know what this means. We know what the formula phi A does. What phi A does is pick up the elements that are isomorphic to A. Right, so this is going to be true of B if and only if A and B are isomorphic, right? Because in this case, if you're assuming that these are isomorphic, then B is the same as A. So it's only true if they are isomorphic. And then that satisfies the back and forth property. Okay, so I'm going to leave that as, we want to leave it as an exercise here. I think that's a good exercise. Because it should be easy enough. Then I has back and forth property. That should be the easy direction. But if you guys believe that this should be true, we can move on and try to write down what that says. So the Scott sentence for A is a sentence that says such that we want a sentence such that B models the sentence by A if and only if I has the back and forth property. Because if we do that, then we have a sentence that holds of a structure if and only if the structure is isomorphic to A. So let me copy all these. To the next slide. Now let me there we go. Okay, so now let's write a sentence that says that I has the back and forth property. I'm going to write down a sentence that says that. Let's see if you remember what the back and forth property is. It's a set of pairs and it has these conditions that whenever for every tuple inside, they must satisfy the same atomic formulas among the first A many. And for every D in B, there is a C in A such that we can find this tuple in I, and the other way around for every C in A, there is a D in B such that this holds. Okay, so we want to write a sentence that says that. So psi A is the following formula. So we're going to say for every, so this is we're going to be looking at this formula inside B. Okay, so we are considering the formula whether it's true or not inside B. So when we quantify over an element, the elements are going to belong to B, right? So we're going to say for every A in A, but we're not looking at formulas inside A, we're looking at the formulas inside B. And for every X, okay, so then this X here, since we're considering up here, this X here belongs X, you have to think of it as belonging to B. Because we're going to apply the formula inside B. So now we have a pair A and X. that supposedly belongs to this set. So what does it mean to belong to the set? It means that this is the case. For every A and for every X, if phi A holds of X, then are we gonna put three things? Well, we need to put the three properties. They satisfy the same atomic formulas. So the conjunction of all the atomic formulas, I'm gonna write these. Okay, so X, I'm gonna write this in English. X satisfies the same length of A many, for the same atomic formulas as A among the first A many, length of A many. Okay, so I don't want to go into much details into this part, but essentially what I'm saying here is they satisfy the same atomic formula. So A is a fixed thing. A is here is inside the index. So we know what A is. So we know which atomic formulas it satisfies. Some satisfies, some doesn't. And we're only considering a few, the first length of A many. So to say that X satisfies the same, we have to put the conjunctions of all the ones that A satisfies and add the conjunctions of the negations of the ones that A doesn't satisfy. Okay, so it's only finitely many formulas. We put them all together. Just copy the ones that that we know are true about A, and we put them there. And ones that are false about A, put the negations there. It's only finitely many. Okay, this is the first part. And we need to do number two. Number two, let's take a look. Now I'm getting faster at this. Number two here says for every B in D there exists a C in A such that happens. Okay. So that's what it's gonna say. It's gonna say for every Y, which again we think of as belonging to B, but this because we're gonna use it in B. There exists a C in A, but we don't quantify over A because we're applying this formula inside B. So we're gonna say these junctions over C in A, this tuple belongs to I. So we're gonna get phi of A, C is true about X comma Y. And the other way around. For every C in A, there exists a Y in B such that phi A, C, X comma Y. And then we need to close. So this parenthesis here is closed here. Okay, so this sentence that I just wrote down says that the relation that you get by considering the tuples that satisfy these has the back and forth property. That's what this sentence says. Okay, so here the X and the Y are the ones that belong to B. And here what we are saying, so in red is the intuition. So here what this is saying is that the pair A comma X belongs to I. And then what this is saying up here and also up there is that the pair AC comma X Y belongs to I. So the red part is intuition, is not part of the formula. Okay, so then this formula is going to be true in B if and only if I has the back and forth property, and I has the back and forth property if and only if A is isomorphic to B. So we get that. So this formula is true about everybody that is isomorphic to A, and exactly about people that are isomorphic to A. If it's true about somebody, that somebody must be isomorphic to A. Cool. All right, so let's definition of these things. Here. So now we can define the Scott sentence rank of A to be the least alpha, such that there is a pi alpha plus 1 sentence that is true only about A. So we just prove there exists one. And then now we can choose this. The rank to be the least alpha, such that the formula can be taken to be pi alpha plus 1. The goal is, the next goal is to show this. Scott sentence rank is the same as the orbit rank. They seem to be quite different. So what's easy is to show the less than or equal. And the other one is going to take some work. Okay, so let's do that. Lemma, the Scott sentence rank of A is less than or equal the orbit rank of A. And in other words, or equivalently, if every automorphism orbit is sigma alpha definable, and therefore the orbit rank is less than or equal alpha, then a pi alpha plus 1 Scott sentence. Right, so this is saying that if here we're saying if the orbit rank is less than or equal alpha, then the Scott rank is less than or equal alpha. That's what that would imply. And therefore this below. This is pretty easy to see from here. It would be good to have a different color. So what I claim here, let's put it, just make it a different color. Claim, let's put it down here. If the formulas phi of A are sigma alpha, then psi A, the big one, is pi alpha plus 1. And well, we need to just count the quantifiers. I don't want to mess this up. Okay, so let me just copy it. Otherwise, so that at least it's clean in this slide. and then we don't mess it up. Oh. Okay. Let's see, let's count the quantifiers. So, okay, so if this one, we are thinking that this one and these ones are sigma alpha, then when you add at this junction or an existential, you stay sigma alpha. But now when you put the for all up front, this becomes pi alpha plus 1. This one becomes pi alpha plus 1. This part over here is quantifier free. This one here is sigma alpha, and I guess it's on the negative. It's on the first side of an implication, so you should count as a. But then here we're only adding a conjunction and for all. So those on top of pi alpha plus 1, this stays pi alpha plus 1 because we are not changing the alternation. Okay, so that's direct from just the form of this. If the definition of each orbit is sigma alpha, then the Scott sentence that we get is pi alpha plus 1. So that's why we get this. So next time we'll show the other reduction, and it requires the type omitting theorem for infinitary logic. So that's also a quite interesting tool on itself. As you can see, there is no obvious way to prove it. I mean, I think you need to go through type omitting to prove the R direction. That there is no essentially there is no simpler formula than this. This is essentially the simplest formula that you can get. I want to do one more exercise. I don't know if I put it as an exercise, or we can do it right now as you want. Exercise, the orbit Scott rank of an ordinal of the form omega to the alpha. We can show with what we have so far is that it's less than or equal 2 times alpha. Actually, it's equal, but we don't have the tools yet to show that it's equal. Hopefully by Friday. Luigi, what do you think? Should we do that now or leave it as an exercise? I think it's a good exercise if I give you a hint.
Okay, you can leave it as an exercise.
Okay, so essentially, I'll give you a hint. So to show that the orbit rank is less than or equal to alpha, you need to show that every automorphism orbit is sigma 2 alpha definable. Now, this is an ordinal. So in an ordinal is rigid. There is no automorphism. The only automorphism is the identity. So the automorphism orbits are just defined by the elements. So you need to show that every element every A that belongs to omega to the alpha itself, or for every A, the singleton set essentially A is sigma 2 alpha definable. There is a formula that is true about it and it's not true about everybody else. And we had some formulas that we did before that were true about ordinals of the form omega to the beta And the Cantor normal form could be useful here to define things that are not of the form omega to the beta. Yes, so omega to the alpha is a well-ordered structure, yes. So the omega is an operation ordinals. So all right, you can tell me how that goes for next time. So the next class is gonna be in 2 days. So on Thursday for you guys, Wednesday for me.
Yes, we have a 1-day break.
You have a 1-day break, and you have tonight for the review session. Let's answer some questions. Any questions from you guys, the students?
Do you have questions? May I ask a question? Do you have a definition of automorphism invariant set?
Okay, let me write it down. I've been using it all the time, but sorry if it wasn't obvious. So R subset of A to the K is automorphism invariant if for every automorphism F from A structure A to itself, R goes to R.
Yeah, thank you.
So it maps up R to R and actually vice versa. Or maybe we can say so it maps R to itself. So that's an automorphism invariant set.
Thank you. Do we have more questions? And if we have currently no questions, then we meet the day after next. And if people have questions, can come to the review section in the afternoon.
Cool. So I will send you the PDF with all these notes
Oh, great.
right now, so you can share it with students.
Yeah, and I will upload it to our website.
Cool. All right.
Thank
See you guys in a couple days.
Bye.
Bye bye.
See you. Bye.